Hello everyone, welcome back. In this video, we will review over key math skills for chemistry, what you will need in this course to feel successful in solving problems. And so this is just an example of being able to interpret a graph. This graph always represents the relationship between two variables, and I'm going to teach you every step of the way how to really analyze a graph in order to extract out key information. So being able to look at the y-axis and understand that, okay, this has volume in liters, and the x-axis, which is horizontal, has temperature in Celsius. And then reading the title, oh, this is telling me the relationship between the volume of a balloon versus temperature. And we can see that that relationship is linear. So our learning goal for this video is to review math concepts used in chemistry, place values, positive and negative numbers, percentages, solving equations, interpreting graphs, and writing numbers in scientific notation. So what do we mean by identifying place values? Well, for any number, we can identify the place value for each of the digits in that number. The place values for two numbers are listed below. So for example, a premature baby has a mass of 2,518 grams. And so what we mean by place value, 2 is the thousandth place. And we know that because you heard me say 2,000. 5 is the hundredth place, so 2,500. 1 is the tens place. And 8 is the ones place. So this is 2,518 grams. In this example here, a silver coin has a mass of 6.407 grams. So once again, the 6 is the ones place, just like we saw here for 8. That's the ones place, the place before the decimal point, if there's a decimal point. And then the place after the decimal point is called the tenths place. The 0 is called the hundredths place. And the 7 is the thousandths place. So for example, it's important in the laboratory to be able to understand place values because you may be asked to report this mass to the hundredths place. And then when you hear, oh, I need to report it to the hundredths place, you know it's to this digit. So in many calculations, we'll have to use positive and or negative numbers. As a reminder, a positive number is any number that's greater than 0, has a positive sign, and often the positive sign is understood. It's not necessarily written in front of the number. So for example, that 2,518 grams in the previous slide, that's a positive number. And notice how we didn't put the plus symbol there to indicate that it's positive. Whereas a negative number is any number that's less than 0 and does need a negative sign in front of it. Multiplication and division, when we're dealing with positive and negative numbers, it's important when like two positive numbers or two negative numbers are multiplied or divided, the answer ends up being positive. So for example, 2 times 3 is a 6. -2 times a -3 also is 6. And you can see that with division too. So when two positive or two negative numbers are multiplied or divided, the answer is always positive. When a positive number and a negative number are multiplied and divided, the answer is always negative. So for example, 2 times a -3 is -6, or a -2 times 3 is -6. So only one of them is negative, which makes the answer negative. Same for division. Now let's talk about addition with positive and negative numbers. When two positive numbers are added, the answer is always positive. When two negative numbers are added, the answer is always negative. So for example, 3 plus 4 is 7, but -3 plus a -4 is -7. When a positive number and a negative number are added, the smaller number is subtracted from the larger number, and the result has the same sign as the larger number. So for example, if I had 12 plus -15, you can say the smaller number is subtracted from the larger number. So 12 minus 15 is 3, but this has a negative in front of it because it's the same sign as the negative number. If we did the other example, -12 plus 15, you still subtract the smaller number from the larger number. So 15 minus 12 is 3, but the sign is going to be that of the larger number, which is a positive in front of the 15. So this ends up being a +3. What about subtraction? When two numbers are subtracted, change the sign of the number to be subtracted and then follow the rules for addition. So for example, if we have 12 minus +5, well, we know that essentially, if it's positive here, then this is just -5. So that's what we mean by changing the sign. So 12 minus 5 is 7. If we have 12 minus a -5, those two negatives will make a positive. So that's changing that sign. So 12 plus 5 is 17. If we have -12 minus a -5, once again, this changes to positive. So 12 minus 5 is 7, but the negative goes out in front of the 7 because 12 is bigger than 5, so -7. And then -12 minus a +5, once again, this turns into negative. So you end up with -12 minus 5, which ends up being a -17. Now you will be allowed to use calculators in my class. I provide scientific calculators for you to use. And on your calculator, there are 4 keys used for basic mathematical operations. The change key or the change sign key is used to change the sign of the number. So when we're talking about positive or negatives, you will have a calculator. So you can always check your work. You can use the tricks that I just taught you in the previous slides, but you could also double check with your calculator. So if you see a +/-, that's the change sign. And then we also have multiplication, addition, subtraction, division, and equals to give us our final answer. Now, whenever you are practicing with the calculators, let me know if you have any questions, because every calculator is a little different. And you can use your own scientific calculators, but once again, you want to get to know it because every calculator is different. So oftentimes I help students figure out how to effectively use their calculator. And so I encourage you to use, if you have access to your calculator, to practice doing these problems to see if you get the correct answer. So for example, if you did 15 minus 8 plus 2 on your calculator, you should get 9. For plus a -10 minus 5 is -11. And then you could also try doing the multiplication and division to see if you're getting the correct answers. And so for example, this is 2 times a -3. And the way you would input that in your calculator is 2 times 3 plus or minus to get that negative in front of the 3. And then you would end up with -6. Once again, if you're ever checking your answers and you get the wrong solution, oftentimes it may not be the way you set up the problem, but rather a calculator error. And so don't be shy, come see me, I can help you out with using your calculator effectively and efficiently. Throughout this course, we will be working with percentages. To determine a percentage, divide the parts by the total, the whole, and multiply by 100%. So let's say hypothetically, I had 32 books on my bookshelf and 8 of them were chemistry books. And then the chemistry books is the part. And the total books is the total, the whole. So percentage is always part over whole times 100%. So 8 divided by 32 times 100% gives me 25% are chemistry books. And then here, if we might also be given like percentage, if the percentage of red balls is 5, it means there are 5 red balls in every 100 balls. So that's what I'm actually going to do and teach you when we do percentages, is that if you're given a percentage, I'm going to tell you we'll treat the whole, whatever the whole is, as 100. And then that means that number is the part. And so 5% translates to 5 over 100. So 5 red balls over 100 total balls times 100%. And like I said, when we do problems involving percentages, I'll teach you these tricks. We'll review over this. But in this particular lecture video, I just want you to become familiar with what percentages tell us. It's the part over the whole. So when we're solving equations, we will need to be able to rearrange them to solve for an unknown variable. So for example, if I have 2x plus 8 is equal to 14, I'm first going to place all like items on one side. So I'm going to move the 8 over here because that's what they look like each other. So subtract 8 from each side. Subtracting 8 from each side helps me get rid of the 8 on the left, and 14 minus 8 is 6. So I'm now 2x equals 6. You then are going to isolate the variable you need to solve for. So divide both sides by 2. And in doing so, the 2 cancels out on the left, and we get x is equals 6 divided by 2, which is 3. You could always check your answer by plugging it into the original equation to verify that your answer is correct. Once again, for any problem I work through a video, I'm going to work through it step by step. I will not be taking shortcuts because I do not want to lose anyone along the way. And at the end of each problem, oftentimes I'll do a sanity check. And I want to be able to show that to you, to model that so you can mimic that when you're doing your problem sets or your assessments as well, as doing that sanity check. Just like this at the end here, checking your answer can help you out tremendously. So let's do an example here. This is a formula or an equation from one of the gas laws. P1V1 equals P2V2. P is pressure, V is volume. And let's say I wanted to isolate P1. I want to solve for that variable. Maybe I have the values for all the other variables, V1, P2, and V2. So what I want to do is isolate it. So in order to do that, what would I need to do? Good. Hopefully you said divide both sides by V1. So that V1 cancels out on the left here, and you get P1 is equal to P2 V2 over V1. As I said on the first slide, it's important that we are able to interpret graphs confidently and extract important pieces of information from it. Remember, a graph just represents the relationship between two variables. So first things first is you always look at what's your horizontal x-axis telling you and what does the vertical y-axis tell you. And so like we saw on the first slide, we were looking at a graph that showed us the volume of a gas in a balloon that was plotted against its temperature. We observed that y-axis represented the volume in liters of the gas in the balloon, and x represents the temperature of the gas. The title indicates that the volume of the balloon was measured at different temperatures. So the title can tell you a lot of information as well. So always read the title of your graph. And then we noticed that different points of data were collected to represent the volume of the gas that was measured at specific temperatures along the way. And so you can see the graph here. And what we notice is that there's a direct relationship between the volume of the gas and the increasing temperature. And we can utilize this graph to determine the gas volume at various temperatures, even if like a data point's not collected at that specific temperature. Like if I wanted to, for example, determine, the volume of the balloon at this specific temperature here, then I could extract that from this graph here. So many of the numbers we work with in this class are either really big or really small. And so we will utilize scientific notation to make the numbers more reasonable. So for example, the number of hairs on our head, there's a lot, right? So there'd be a lot of zeros making a really big number. But rather, instead of writing that, we would just simply state that there's 1 times 10 to the 5th hairs on the scalp, and that each hair is about 8 times 10 to the negative 6 meters wide. So it's very tiny. So that's a big number. This is a small number. You can see we're using what's called scientific notation to represent those numbers. Now, numbers written in scientific notation have 2 parts. They have a coefficient and they have the power of 10. So let's write 2,400 in the correct scientific notation. So what we do for the coefficient is we will write down the first non-zero number, so that's 2. And then after that non-zero number, we will write a decimal point. And we will include 4, because it's also a non-zero number. And we'll just leave it at that. I won't get into significant figures just yet, but we're not going to include the zeros. We're just going to include the 2 non-zero numbers, 2 and 4, and you always put the decimal after the first non-zero number. This is called your coefficient. And now we have to the power of 10. So what I like to do is I take the original number and I put my decimal point here, and then I see how many spaces I have to move to the right to make it that big. So in this case here, I had to move it 1, 2, 3. And so it's to the power of 10, 10 to the 3rd. So when we make a number bigger, from 2.4 to 2,400, we move it to the right, and the exponent is going to be a positive number. You will see when it's a really small number, we will have to move the decimal to the left, and the exponent will be negative. So here are some examples of numbers and how to represent them using scientific notation. So these are just some powers of 10. These are bigger numbers. So for example, 10,000, I would start my decimal here after the non-zero number and move it 1, 2, 3, 4 places. And notice how it's 1 times 10 to the 4th. For this one, I would start here, 1, 2, 3. So 1 times 10 to the 3rd, so on and so forth. For really tiny numbers, it's the opposite. So what I would do is I always have to move it to the left. So if I had the decimal here, I have to go over 1. And if you're moving it to the left, then you have a negative number. So I moved it to the left. So this is 1 times 10 to the negative 1. Start, as always, to the right of the non-zero number, that first where the decimal place would be, and then move over 1 and 2. So then that is 10 to the negative 2. 1, 2, 3, 10 to the negative 3. 1, 2, 3, 4, 10 to the negative 4th. So the small numbers get negative exponents. So let's go ahead and write the diameter of the chickenpox virus in scientific notation. You can pause the video right here, try it yourself first, and then check your work with me. All right, so if we put the decimal point here, how many spaces did you have to move over? Let's count. 1, 2, 3, 4, 5, 6, 7. So write the non-zero number 3 times 10 to the -7th, and make sure you always include units if there are units. So this is in meters. So once again, this is 1, 2, 3, 4, 5, 6, 7. So 3 times 10 to the -7th meters. Here are some measurements that are written in scientific notation. So for example, the diameter of the Earth, this big number, that's 1.28 times 10 to the 7th meters. The mass of a typical human, 68 kilograms, so 6.8 times 10 to the 1st kilograms. The mass of a bacterium, Mycoplasma, is 1 times 10 to the -19th kilograms. So we will be using scientific notation quite often in this class. Now in your calculators, numbers in scientific notation can be entered into the calculator using the EXP or the EE key, depending on your calculator. So be looking for that on the calculator you're using. And so even though your calculator may show it, for example, 2.5 e to the -4th, it still has it programmed into the calculator as 2.5 times 10 to the -4th. So you don't need to type it in 2.5 times 10 to the -4th on your calculator. Use the EE or EXP function to do that for you. So let's go through the guidelines for writing a number in scientific notation. So step 1, move the decimal point to obtain a coefficient that is at least 1 but less than 10. So that was me telling you non-zero number, put a decimal point right after that. That will keep your coefficient between 1 and 10. You're going to step 2, express the number of the places moved as a power of 10. Remember, if it's a large number, the exponent will be positive. If it's a small number, the exponent will be negative. Step 3, write the product of the coefficient multiplied by the power of 10 in the end. So for example, 2.5 times 10 to the -4th would be how you represent scientific notation. So let's pause right here. Pause your video so you can do the study check. Check your knowledge of writing in scientific notation, and join me again to check your work with me. All right, so let's see what you got. So the first one, 64,000, I would put the decimal right after the first non-zero number, which is 6, and then I'd have to move it 1, 2, 3, and 4. So you would write the coefficient 6.4 times 10 to the 4th. Good. Hopefully you kept that as a positive exponent there. And there's no units, so no need to write units down for that one. So 6.4 times 10 to the 4th. And then for this one here, we would put the decimal after the first non-zero number, which is 2. We'd have to move to the left. And so in that case, this is 2.1 times 10 to the -2, because we moved it 2 spaces over. This is a really small number, so negative exponent. And let's just review over the concept map for this first module and understanding chemistry in our lives. In the first video, we really talked about substances called chemicals and understanding what is a chemical. We then, in the second video, discussed the scientific method, which starts with observations and leads to a hypothesis, experiments, and conclusion. But remember, it was cyclical. Sometimes we have to reevaluate our hypothesis after running experiments. We then discussed how to best learn and master chemistry. by actively learning, reading the text, practicing problems, self-testing, and working with a group, and asking me questions. And then in this video, we went over some key math skills that will help you be successful in this course by looking at identifying place values, using positive and negative numbers, calculating percentages, solving and rearranging equations, interpreting graphs, and writing numbers in scientific notation. Thank you for watching this video, and as always, email me with any questions.